Hi everyone, my name is Shmuel Berman. Today I'm going to be giving a presentation for Conflict 2021 on intra-update sniping vulnerabilities in smart contracts regarding smart contracts, and these are the smart contracts, the blockchain ones. I'll explain all the necessary background in a little bit, but basically I'll be explaining how what intra-update sniping vulnerabilities basically being, vulnerabilities that arise when you try to update large-scale systems. The vulnerabilities I'll be talking about are kind of relevant to a lot of large-scale infrastructure. In fact, a lot of this work, and actually almost all the work, is based on IAHA and the AWS paper, which Julian presented, I believe, before. But I'll be rediscussing all of that now. And yeah, let's get straight into it. So the first thing we have to know is just about the concept of a blockchain, right? Which is kind of this trustless consensus system for transactions, for contracts now. It started out as just transactions in a way that I can send money to a different person without there being a central authority to guarantee that I sent it and they only receive it and no one else can spend my money, right? We want to be able to do that just between us. And the way we do that is we have different parts of the system ensuring compliance, right? Where we want everyone to act in their own best interest. You have miners who are constantly trying to mine a new block, and a new block is kind of when I am able to get my transaction through, right? You have to wait for the next block. I can send money to Alice now, but that money won't officially be sent through until the next block, and a miner includes it in that block. Mathematically, what that means is not so important here. What's important to know is that transactions and updates to any contracts or anything on the blockchain occur in increments, right? We can't send things out as we please. We can only guarantee that things will be updated in a discrete manner. In this diagram at the bottom, I have block 1, block 2, and block 3. And the time in between these is different, which is also important, right? We know what the average time is for Bitcoin and Ethereum. We don't know how much the actual time will be. So if I want to do 10,000 transactions right now, and a finite amount fits between each block, right, fits inside of each block, meaning let's say, this is not true, but let's say each block can hold somewhere between 4,000 and 5,000 transactions. I can't guarantee that all my transactions will be on block 1. I can't even guarantee they'll be in 10 minutes. I can't guarantee they'll be in 20 minutes because maybe a miner has choice over which transactions they include to a point. So if I want to send an update to the blockchain, no matter which one it is, I have to wait a certain amount of time to know that it will go through. If I send 2 updates, I can't know when they will go through, in relation to each other, and I don't know at what point I'll be able to send them. That's some important background information. Next thing we want to establish is the existence of smart contracts. Before we talked about sending money. Alice wants to send $5 to Bob. Bob wants to receive it, right? That's very simple. And now what we want to do is have logic encoded in the smart contract, which is an agreement between Alice and Bob, for instance, that is facilitated by this trustless system. They can know for sure that the money will be held in escrow, so to speak, unless Bob fulfills certain conditions as specified by a smart contract. They can interact with non-blockchain code, which means that obviously you can't really code certain parameters that exist in real life. Like if a package is delivered and then Bob pays, there obviously has to be some interaction with the real world, which can be a cause for vulnerabilities. But that makes the system much more powerful in that we can have conditions like that, which are obviously bypassable on the non-smart contract or non-blockchain portion of the code. But it kind of contributes to this level of infrastructure that has to exist for smart contracts to be used. Because what you can do actually just on a code base on a blockchain is much less interesting, even if it results in new coins, new cryptocurrencies. Well, that's interesting. The large scale infrastructure comes from, let's say, having Amazon deliver a package and then you pay. And if you don't get the package, you don't pay, or other such agreements between companies, and that could be a smart contract. The next thing we have to note here, the important point on this slide, is that like transactions, the changes are pushed permanently only with the next block, which means that if I want to update a variable in a smart contract, let's say there's a Boolean representing if I paid or not, right? And if I don't pay, then I don't get interest for the next 10 years, because let's say it's a smart contract that facilitates loans, right? When I pay, that update will not come to the blockchain until the next block, which accepts my transaction. At minimum, that's the next block, but it could be in 2 blocks if my transaction is not accepted immediately. I do not know when that change will be accepted. Now, for contracts like Ethereum, for smart contract platforms like Ethereum, where the block time is 13 seconds, it doesn't really matter because not much can change in 13 seconds, 20 seconds, 30 seconds. It's very quick in terms of when you're actually transacting. You usually don't need, especially on the smart contract, because it's really expensive to run code anything faster than that. But this will come into play when I discuss the vulnerability in 1 second. The next interesting thing we have to talk about is upgradable smart contracts, because one of the main pulls towards blockchain is its immutability, right? If I send $5 to Bob, right, then I can't get that money back. He can send it back to me, but that transaction, once it's accepted, of course, by a block or by the blockchain, which on Bitcoin is 6 blocks. Even though it's very rare for 1 block not to be sufficient, and that has to do with security. That's outside of the scope of this discussion. Once it's been accepted by the blockchain, then it's done. It's just the transaction will always exist on the ledger. Similar thing exists by smart contracts. Although the variables can update, and they will update according to the logic of the contract, you cannot update the actual logic. Like if I make a typo and I wrote if their ownership level is over than 2, and I actually meant 100, I'm not going to be able to change that. So the question becomes, when we have these large-scale blockchain infrastructures, like we talked about with Amazon before, there's going to be a lot of moving parts, or a lot of things that could go wrong. We want to be able to actually upgrade that infrastructure. And although a lot of that could take place outside the blockchain, the code base is a check if the package has been delivered, etc. We also want to be able to upgrade smart contracts on the blockchain itself. We want to be able to update that logic. So someone came up with a very clever idea, and this is popular even nowadays, although it's not so commonplace as I think it will be in the future, is the idea of a smart contract proxy, which means that we're going to have a proxy contract which implements variables, and then we're going to have an implementation contract, right? Now, neither of these contracts can be changed in their logic. You might ask, how is this possible? The way it works is the proxy will obviously have the variables, and then it'll have one variable which will be contract like number. Every single contract has an address. So it'll delegate the functions to the implementation contract, and every user will only interact with the proxy contract. So when they interact, the proxy, like let's say they try and call a certain function in the proxy will delegate that function to implementation, and the implementation function will actually have, like, let's say it's withdraw money, it'll implement like the authenticating part, et cetera, et cetera. It'll store all that contract logic. And obviously you can change a proxy contract to make a function that allows you to change the contract address of the implementation, because it's just a field. You can say, if you're the contract owner, then like it checks that, and then you can change the contract address to whatever you want. This is cool. Because now it's much more interesting. We can have larger systems, and if you make a typo, it's not so bad. The implementation contracts can't be changed, but what we can do is deploy an entirely new contract and then switch out the proxy contract's implementation address for the new contract which we just made. Obviously, that can become complicated as we make larger systems, and when I get to our vulnerability in 1 second, it'll become more obvious why we'd want to model our system as a configuration file. Same thing happened with AWS. And as these web servers, as the web became larger, right, you have this idea that like we want to be able to look at the system instead of as a lot of individual code, which is very confusing. We want to be able to simplify it in order to look for vulnerabilities, in order to see our system as a whole. So I've drawn a sample system here, which is just a user interacting with some private methods, and they're being authenticated at one point. Meaning if they have a certain qualification, maybe it's a blockchain address that belongs to a certain class, maybe it's a certain stake in a company, like they have a smart contract, they've donated enough money to it that will be taken out by the company at a certain point, then you're authenticated. So it doesn't matter what the actual functionality is. All that matters is that this contract system, where each of these bubbles is a smart contract, can be modeled in this JSON configuration file which I made here. This is, by the way, totally arbitrary. In the future, I assume the configuration files will need more information, but this contains all the information that will be necessary for discussing the vulnerability. And now I'm just here to explain what it means. This just means that the connection security is 1, connection security is 0, meaning if we go back to the prior slide here, once we access A, which can access B, we're not authenticated again, right? And this will come into play as when I explain the actual intra-update portion. When we're updating the system, how does the vulnerability arise? Okay, so let's explain what the vulnerability is actually. So that's why we have a very innocuous system here, which is sample system, right? We have a proxy for an authenticator. The authenticator contract is a contract that will check a certain condition to make sure you can access a method. And that corresponds to this connection security field, which we talked about there. We might want to change the authenticator so we have a proxy attached to it. Maybe one day we want to check if you're richer, you have more than 500 Bitcoin or 500 Ether in your wallet. Maybe the next day it'll be 250 if the price goes up. And then we'll have another proxy for a function. This function will be see someone's wallet balance. It'll be printed out or something in a terminal window. Don't know what it is. Doesn't matter. All that matters is now we want to change the system to sample system v2, which is now if you're an account owner, you can withdraw funds. Right, and that makes sense, right? If I have like an account online, so there's some sort of smart bank, they check if I'm the account owner, which I guess is a simple variable check, and if I can withdraw funds into my wallet. The bank, maybe you earn interest or something, I'm not sure. Anyway, we want to upgrade from that system to the other one, from sample system v1 to sample system v2. You might be able to see the obvious problem that exists here. We want to push 2 changes to the blockchain. We want to push one for proxy for this first proxy and one for the second proxy. Where the first proxy we want to change from authenticator 1 to authenticator 2, and for the second proxy we want to change from function 1 to function 2. The problem is we don't know which one will be updated first, right? It's possible that the first proxy will be updated first and the authenticator will change to account owner. It's possible that the function will be updated first and then it'll be updated from seeing balance to withdrawing funds. If the function is updated first, we're still not authenticated on the first function. So the first function, the authenticator 1 lets anyone through, as we said before. Anyone can see someone's wallet balance. So if we have authenticator 1 with function 2, and this intermediate stage, let's say the first block only accepts that update, and the second block hasn't happened yet. It's only been like 15 seconds on the Ethereum blockchain. Then we have the state where anyone can withdraw funds. This will only be probably in effect for less than a minute on Ethereum, just statistically speaking. But that is a huge vulnerability that can exist, even though both our initial and final systems are both secure. That's important. I'll repeat that. Both our initial and final systems are perfectly secure, but we have intermediate state, which does not exist for an infinitely long amount of time. It only exists for a small amount of time, but you can use that to violate the security system and withdraw funds. And we know that there have been bigger stretches in the crypto community before for overcoming the security that companies try to create and kind of taking advantage of the immutability. So what I've done here is I have made a Python tool called Sancus. It's public, it's on GitHub. This is kind of based on the Hayaha work that Julian made, and he also presented before, and he did it in relation to AWS. It takes in a configuration file, 2 configuration files that of this form that I made before, and it makes an upgrade state graph, right? Where an upgrade state graph is kind of this graph that exists as like a symbolization of every intermediate state that can exist, which I'll show in just 1 second. Then it will test if every single node in the graph maintains that security level. Meaning, if the security level has level 1 at the beginning and then 1 at the end, right? Then we want to make sure for every, or let's say it has 3 at the beginning and 3 at the end, we want to make sure it maintains that the entire way through. And the way it's going to solve this, as you can see here, this is a very secure, this is a very easy problem to solve. All we have to do is update function 1, and then check, proxy 1, and make sure the authenticator updates, and only then do we push function 2 change. In a large scale system, it will not be so simple to see which one to update first. So what this does is it tells us do we have any dependencies? Because maybe we can just push all of them at once and there's no problem. If there are any dependencies, tell us, okay, you can push all of these first, right? And then you have to push these. And if it doesn't mention something, it doesn't matter what order you push it in. You can push it in any order. Like I said before, this is based on Julian's work analyzing infrastructure as code to prevent intra-update sniping vulnerabilities. The math is similar there. Won't be talking so much about that here. So yeah, let's move on to the upgrade state graphs. Okay, so here we have an example of an initial and target state, right? Where we have 4 different methods, right? We have C, B, and D, right? And they have various statuses as private and public, and we want to update them from one contract to another. One state to another, where B is now implemented differently. And keep in mind, these are all proxy contracts. So we can update every single one of these as we see fit. So B private and B public are the same proxy contract with different implementation contracts. Importantly, when I write diagrams like this, the letters indicate that they are the same proxy contract. Okay, fine. So I have 2 configuration files here. And we want to update from state 1 to state 2. Now, it's not so simple to see what the actual vulnerabilities are in this case, because I guess it's not so hard to see, but we're updating from a secure one to an insecure one. So it's different from before we were one that is secured to one that is not secured, meaning the second one, the target state that we're upgrading to, the methods are all public. In the initial state, some of the methods are private, and we have an authenticator. So we want to upgrade from one state to the next, but we don't know what order our updates will actually be pushed live to the chain. So that we run the tool, and what does it get us? It gets us an upgrade state graph. What this does is it enumerates every single possibility, realistic possibility, that the graph will display. Right? I mean, sorry, that the upgrades could go through. That this if we represent this as a list of states of every contract, so we can have either B public, we saw before, B public is a target, B private is the initial, and B private is connected to D, whether it's meaning B is connected to D, whether D or B is public or private. So we can have B public connected to D private connected to D public. And from this, it's easy to see with your own eyes where the vulnerabilities are. If B updates first and D is still on private, then B public, which is not authenticated, unlike B private, can access D private, and we're violating the security of our system. So what the Sancus tool does is it will build this upgrade state graph from the initial and target states and then analyze it by propagating security levels, right? Where for the sake of our implementation, we made it linear, cardinal, I think, actually, where that you always have a numeric value, meaning 13 is higher than 4. But there's no reason why we couldn't propagate more complex security variables like security level A or L. If you look at the code base, it's only like that. But the thing to realize here is that every single state here, every single contract has a security level, and in the initial and target states, and we want to make sure it does not go below the least of those 2. Because B public will, and obviously B public will have a different one than B private, because B private actually is authenticated, but B public does have an authentication level of 0, and B private has one of 1. And C public, for instance, in this graph, even if we change the implementation, the security level doesn't change. So we don't analyze it. We don't care what's inside of it. And again, just stating this again, in this case, or in every case rather, we want the initial and target states to both be secure. If they're not secure, this tool will not work. Now this is the above here gives us conditions for being secure, and this is taken out of Julian's paper. So if we look at this graph from before and we propagate the security level, let's say B public has 0 and D private should have 1, but it actually only will have 0 because B public can access it. That's when we know that in the upgraded version, it's less secure, and then we'll report a dependency there. It'll tell you, no, update a different node first. For instance, if we want to update from B private, we don't want to update from B private to B public first. We want to update first D to D public. We know if there's a vulnerability, it will be found, and it gives a suggested order for the ones that matter, how to update it. So it's a very powerful tool. Now, I think this, that's the end of the presentation, but I think this is important, not because of the infrastructure that exists nowadays. I think in the future, it'll be a lot more significant when we have large-scale blockchain infrastructure. A lot of the use cases of smart contracts are more theoretical now. But as they begin to interact with the real world, and we do need to support large-scale infrastructure, we've seen other large-scale infrastructure kind of trend towards abstracting it away into these configuration files, and kind of that's how we update things, specifically like with AWS, as I talked about before. So I think it's important to realize that the similar vulnerabilities that affect those systems can also come into play here, given what we know about blockchain. And these vulnerabilities can be solved with just a little bit of analysis. Thank you for listening. My name is Shmuel Berman, and yeah, I hope you enjoyed.